Let's start by finding a derivative of a constant function. Remember, a derivative of a constant function is just a horizontal line. So it'll take the form y equals some number. And because the slope of a constant function is always 0, whenever we take the derivative of a constant function, we're always going to get 0. It's a 0 function. So for all of these, I'm rewriting them in as derivatives, but for each one, our derivative function would be 0. This last one's a little bit trickier. I'm assuming that the independent variable is x, and so I'm assuming that that k is just a constant, so it's some constant times pi divided by 2. The single variable rule is basically saying if all we have is a variable, like y equals x is an example, that means that the slope of that function, well, first of all, it's linear. It's a line, and the slope of that line is just 1. So for each of these functions, our derivative function would just be 1, a horizontal line at 1. Because everywhere on each of those functions, the slope is 1 at every point on those lines. This is where it gets a little bit more interesting. We have the power rule. The power rule says that if you have an exponent on x, what you can do is move that exponent to become the new leading coefficient when taking the derivative, and then subtract the exponent by 1. So let's look at that on A. So if I'm taking the derivative of this function, the exponent of 2 becomes the leading coefficient, and then I'm going to take 2 minus 1, and that's going to become my new exponent. So the derivative of y is 2x to the first power. So similarly, on f, my derivative of f, that 4 becomes my leading coefficient. X to the 4 minus 1 is third power. For C, before I get going, I'm going to rewrite the square root of x as x to the 1/2 so that I can use the power rule. So the derivative of y, that 1/2 becomes my new leading coefficient. 1/2 minus 1 is negative 1/2. In my final answer, I don't want to have any negative exponents, so I'm going to rewrite that. I have a 2 in the denominator, and then I'm also going to move that x to the negative 1/2 to the denominator, so it's x to the positive 1/2 down there. For D, 1 over x is the same thing as x to the negative first power. We can move that x to the numerator and give it a negative exponent instead. It means the same thing. And now that it's written that way, we can use the power rule. So that negative 1 gets moved as the coefficient. Negative 1 minus 1 is negative 2. And I can rewrite that then as negative 1 over x squared. So similarly with E, I'm going to rewrite it as x to the negative second power. So the derivative of f is negative 2x to the negative third, or negative 2 over x cubed. On f, it's the same idea. We just have a rational exponent. That's x to the negative 2/3. So my derivative would be negative 2/3 x to the negative 2/3 minus 1 would be negative 5/3. And then again, I'm going to rewrite that so I don't have negative exponents. Negative 2 over 3x to the 5/3 power. Our next rule is the general power rule, and it actually works very similarly to just the power rule. The only difference is there might be a leading coefficient already. And if that's the case, we multiply the exponent by what's already there. So for A, what that looks like is multiplying the 2 times the 3 when taking the derivative to get 6x, and then similarly, we're going to subtract 1 from the exponent. So the derivative function of 3x squared is 6x. When we take the derivative of s, We take negative 5 times 3 is negative 15t squared when we subtract 1 from that power. Before I do c, I'm going to rewrite that as 6x to the 1/2. So when I take the derivative, 1/2 times 6 is 3. 1/2 minus 1 is negative 1/2. And then I'm going to rewrite that so that there are no negative exponents. I could also write that as 3 over the square root of x. Either one would be acceptable. D, I'm going to rewrite before I get started as 3x to the negative 2nd power, so I can use the power rule. When I do, I get negative 6x to the negative 3rd, or negative 6 over x to the 3rd. F can be rewritten as 4x to the negative 1/2 power. So the derivative of f would be negative 2x to the negative 3/2 power. And again, I'm going to rewrite that as negative 2 over x to the 3/2. Last example here, rewrite it first as negative 8x to the negative 4/3 power. When I take the derivative, negative 8 times negative 4/3, that's 32/3. X, when I take negative 4/3 minus 1, that's negative 7/3. And I'm going to rewrite that as 32 over 3x to the, 7/3 power. So that's the power rule. The cool thing about the sum and difference rules are if you have multiple, or a function with multiple terms, you can basically just take the derivative of each term individually. So on this first example, f, I'm going to take the derivative of x to the 3rd power using the power rule. That's just 3x squared. Then I'm going to take the derivative of negative 5x squared. That's negative 10x. Then I'm going to take the derivative of 2x, that's just 2. And then I'm going to take the derivative of the constant, which is 0. So B, I'm going to do the same thing. Just take it one term at a time. So first we'd get 2x to the 4th plus 4x to the 3rd plus 6x plus 0. For C, I'm going to rewrite that first as x to the 1/3 plus 5x to the 1/2. And so when I take the derivative, I get 1/3 x to the negative 2/3 plus 5 over 2 x to the negative 1/2. That got kind of messy. Let me rewrite that so we have no negative exponents. So 1 over 3x to the 2/3 plus 5 over 2x to the 1/2. I'll just leave my answer like that. D looks pretty good. I'm going to rewrite 4 over x as 4x to the negative 1st power before I get going. And then the first term, when I take the derivative of that, we get 15/2 x to the 1/2. Then we get negative 10 x to the 2/3. And lastly, we would get negative 4 x to the negative 2nd. And that last term would need to be rewritten as negative 4 over x squared. Oh, a couple more of those. Let's look at this one. So I'm going to rewrite this before I get going. We have 3x squared can stay 3x squared, but then we have minus 4x to the negative 2nd power and 2x to the 1/2 power. So when I take the derivative of each of those three terms, the first one is 6x, the second one is 8x to the negative 3rd, and the last one would be 1x to the negative 1/2. And rewriting that We have 6x plus 8 over x cubed plus 1 over x to the 1/2, or 1 over the square root of x. And the last one, in order to use the power function, or the power rule, sorry, I'm going to start by dividing each one of those terms by x. So 8x cubed divided by x would be 8x squared. 4x squared divided by x would be 4x. And then minus 3 over x. And I'm going to rewrite that as minus 3x to the negative first. And then same rules again. 16x plus 4 plus 3 over x squared. The next thing we have is the derivatives of the sine, cosine, and tangent functions. What they want you to look at first is noticing these graphs. So this is the sine graph. This is the graph of cosine. And if you notice my sine graph, if you notice my slopes, I'm increasing until pi over 2. So that's a positive slope. And then I have a slope of 0 at pi over 2. And then I'm decreasing, or negative slope, until 3 pi over 2. And then I have a slope of 0. And then I'm increasing again. Well, if you look at the cosine graph is the slope graph of sine of x. So we have positive until pi over 2. Then we have it at 0, just like in our sine graph. The slope of the tangent line right there is 0. Then we're decreasing, which means it's negative, which means it's underneath the x-axis. Then we hit 0 again at 3 pi over 2, just like the slope of our tangent line for sine is at 3 pi over 2, and so on. And so the derivative of sine of x is cosine of x, because the graph of cosine is actually the slope graph to sine. The next couple of pages of the notes actually walks you through how to prove these derivative functions for sine and cosine. But for now, I just want you to memorize that the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. And then the derivative of tangent of x is secant squared of x. But they walk you through how to do that here on those pages. And then down here at the bottom again, it says the derivative of sine of x. Again, that's cosine of x. And the derivative of cosine of x is negative sine of x. Here are a couple other things that you just need to memorize. The first is the function e to the power of x. The derivative of e to the power of x is just e to the power of x. That's just something you need to memorize. Also, the derivative of ln of x is 1 over x. That's another thing that you're just going to need to memorize. To do derivatives with these log functions, one thing that you'll have to remember is those log properties that we do in Algebra 2. So one of the log properties, called the power rule, says that when there's an exponent, we can move that in front. So ln of x to the third power is the same thing as 3 ln of x. And we know that the derivative of ln of x is 1 over x. So the derivative function of this would be 3 times 1 over x, or 3 over x. So using those log rules again on this next one, one of our log rules, log properties, I should say, is if we are multiplying, right? if we're taking the log of a product, we can use the product rule, which says that this is the same thing as ln of x squared plus ln of e to the x. And this is the same thing. So I'm just simplifying g. I'm not taking the derivative yet. This is the same thing as 2 ln of x plus x ln of e. Right there, I'm using the power rule. That was one of those properties. Oops, ran out of room. Now, ln of e is just 1. And we know that to take the derivative of ln of x, that's 1 over x. So now that I'm taking the derivative, I have 2 times 1 over x, which is 2 over x, plus the derivative of x, which is just 1. Let's try another one. The next one, before I do anything, I don't have any log properties I need to apply here, but I'm going to rewrite this as ln of x minus x to the negative first power. So when I take the derivative of ln of x is 1 over x. And then the derivative of negative x to the negative first power is positive x to the negative second power. Or when I rewrite this, I get 1 over x plus 1 over x squared. We have some more properties to apply on this next one. This is a quotient. We're taking the log of a quotient, so we need to use the quotient rule. Our quotient rule says when we have division within logs, we can expand it by subtraction. So I can rewrite this as ln of 2e to the x minus ln of 3x. And then here I have a couple products. So now I'm going to use the product rule and do ln of 2 plus ln of e to the x minus ln of 3 minus ln of x. I probably should have done that all in one big swoop, is what I probably should have done. Done that quotient and product rule all at the same time. But now we're going to calculate each one of these. So ln of 2, that's 0. That's just a constant. And the derivative of a constant is 0. So we have 0. Same with this one. Ln of e to the x, I probably should have written that using the power rule. I can rewrite that as x ln of e. And ln of e is just 1. So really I just have x there. And so now when I take the derivative, I'm taking the derivative of just x, which is 1. And then this is 0, this is 0. And then I'm taking the derivative of ln of x, which is 1 over x. That was one of our rules. So that's our final answer. All right, 2 more. We've got the product rule and the power rule going on here. So I'm going to first start by rewriting f using log properties. So this would be ln of 4 plus 3 ln of x. I'm using the product property and the power property there, plus x ln of e. And again, ln of e is just 1, so that's just x. Ln of 4 is a constant, so when we go to take the derivative, that's going to be 0. That's just 0 when we take the derivative. This derivative is 1 over x, so we have 3 over x, and the derivative of x is just 1. And then one more. We have pi times e over x. Can't simplify that anymore. I am going to rewrite this as x to the negative 2/3 power. When I take the derivative of pi times e to the x, remember the derivative of e to the x is just e to the x. Derivative of that is just e to the x. So the derivative of pi e to the x is just pi e to the x. When I take the derivative of the second term, I get positive 2/3 x. Then I need to take negative 2/3 minus 1. We're using the power rule here, which is negative 5/3. So our final answer would be pi e to the x plus 2 over 3x to the 5/3. Woo!